going to discuss the twin paradox. If you've seen videos on the twin paradox before, you've probably noticed that people give conflicting explanations to it. So to confuse you even more, I'm going to give you another explanation. What were the conditions that led to the twin paradox? So if we're going to talk about the twin paradox, we'll need a couple of twins. So here they are, Bob 1 and Bob 2. I think this guy's name is Mark, but we're going to call him Bob. The story begins in the 19th century, and back then, people divided things up into particle-like and wave-like. Things either behaved like a particle or they behaved like a wave. We know today from quantum mechanics that almost all things sometimes act like a wave and sometimes like a particle. The electron, for example, can be wave-like in certain circumstances and environments, or it can be particle-like in other circumstances and environments. But back in the 19th century, people didn't know anything about quantum mechanics for the most part, and so they divided things up into particle-like and wave-like. How are particles different from waves? Suppose we put our twins in outer space. We'll put Bob 1 over here, and he's just floating in space. We'll put Bob 2 in a rocket ship. He comes along here, and when he gets to this point, it shoots a missile or a bullet or something from here to here, and we want to know how long it takes the bullet to go from here to here, a distance x. Well, since we're in outer space, far away from any gravitational effects, we can use this really simple formula to compute the distance in terms of the time. So if we want to know the time, t, that's equal to x over v. We can solve for v2. We can say that dx dt is equal to v. Mathematicians put these little d's in front here because they call it the derivative to confuse us, but all this really says is that v is a constant. For the whole video here, v is going to be a constant. What was the difference between particle-like and wave-like? Bob comes along here and shoots a bullet. The ship and the bullet are particle-like. The velocities are additive. So in order to get the time it takes the bullet to go from here to here, we have to add the velocity of the ship plus the velocity of the bullet to get the total velocity. Let's say that x is equal to 200 feet. Vs is equal to 25 feet per second. And Vb is equal to 25 feet per second. Then t is equal to 200 divided by this plus this, which was 25 plus 25, which is equal to 200 over 50, which is equal to 4 seconds. So it would take 4 seconds for Bob 2's bullet to go from here to here. In Bob 1's case, Vs is equal to 0. So we just divide by the velocity of the bullet, and that would be t. So this is Bob 2, this is Bob 1. That would be 200 over 25, which is equal to 8 seconds. And so it would take twice as long for Bob 1's bullet to go from here to here as it would for Bob 2's bullet to go from here to here. What about wave-like? If we repeat the same experiment and send Bob 2's spaceship along here, and when he gets here, he shoots a sound wave from here to here, and Bob 1 does the same thing. He shoots a sound wave from here to here, what would happen? Nothing would happen. It wouldn't go anywhere because sound waves need something to travel through. And since we're out in outer space, there's nothing here to travel through, and so sound waves wouldn't go anywhere. We'd have to, in this box, we'd have to put air, water, or something for the wave to travel through, and the velocity of the wave would be wholly dependent on the substance that it was traveling through, like water or air. In Bob 2's case, if he shot a sound wave from here to here, and there was just air in that little box, then it wouldn't depend on the velocity of the spaceship. It would only depend on what substance it was traveling through. Velocity of Bob 1's sound wave and the velocity of Bob 2's sound wave would be exactly the same. And in this case, from his perspective, we'd have to subtract the velocity of the spaceship. So this was not the same as this. So to sum up, particles are additive in their velocities, and particles can travel through empty space. Waves are not additive in their velocities, and they can't travel through empty space. So that was the difference between particle-like and wave-like from a physics standpoint. So there's a couple of different kinds of waves that we should be aware of. There are transverse waves and longitudinal waves. What's the difference? Here's the disturbance in the medium, so the wave moves along like this, and the disturbance in the medium, or air, or whatever substance it is perpendicular to the direction of the wave, the propagation of the wave. In the longitudinal case, the disturbance is parallel, and so it goes like this to the direction of the wave. So it kind of compresses and uncompresses, compresses and uncompresses. That's the difference between transverse waves and longitudinal waves. Light is a transverse wave. Sound is a longitudinal wave. The big debate back in the day was whether or not light was a wave or a particle. And the great physicist Isaac Newton thought that light was corpuscular. He argued that since you could shine white light through a prism and all these bands came out in straight lines, that light was particle-like, because waves didn't travel in straight lines. The refraction and reflection properties of light seemed to indicate that light was particle-like. But in about 1803, Thomas Young, an engineer, shined light through two little slits, and on a detector screen over here, it showed alternating light and dark bands. And that was characteristic of wave behavior. Particles didn't act like that. And so it showed these interference patterns. What's an interference pattern? Maybe we better tell you what that is. If you have a wave here and another wave, like this. Now note that when the wave comes in, it goes through the two little slits, makes two waves, and when a crest of one wave meets the crest of another, you get these light bands where they reinforce, or a trough meets a trough, you get these bands that reinforce. But when the crest of a wave and the trough of a wave line up, then you get dark spot. They cancel out, indicated by the dark bands here. And in about 1865, Maxwell showed that light was an electromagnetic wave. Well, if it was an electromagnetic wave, it had to have something to travel through. How did the light get from the sun to the earth, for example? Because waves couldn't travel through empty space. At least that was the thought at the time, the belief at the time. And so everybody thought that there was a luminous ether, the light waves travel through, so that light could get from the sun to the earth. And everybody sort of assumed that, I wouldn't say everybody, but most people assumed that luminous ether exists, and nobody really bothered to check. But in about 1887, two American physicists, Albert Michelson and Edward Morley, decided to test to see whether or not the ether actually existed. Let's look at the rationale that Michelson and Morley used to build a device that would ultimately test whether or not the ether actually existed. The ether was assumed to be stationary, and so if you have the Earth here and it's moving through space, then that creates an ether wind like this. It's like being in a stream. If you have a little boat here, you're rowing a boat, you want to know how long it's going to take you to row from A to B and back again. And we'll just call that distance A for right now. Just give it a name. We'll just call that the time to go from A to B. So in the first leg of your journey, the time would be the distance divided by the velocity. Well, what's the velocity? You're rowing at a speed c, this speed, but you're bucking the stream. Your velocity is c minus v for your first leg. And then when you come back, you have to add a distance a and then divide it by the velocity on the way back. But this time you're rowing with the current, so it would be c plus v. That's time to go from A to B and back again. What if you're rowing in this direction? If this distance is also A, what is TAC? We'll have to use the Pythagorean theorem for this because the direction of the flow is perpendicular to the way you're rowing. So you kind of have to aim your boat out this way because the stream is going to push you over this way. But we will call this distance here AC, that's that distance, v prime. And so if we use the Pythagorean theorem, we'll get v prime squared plus v squared is equal to c squared. This is the hypotenuse of a right triangle. We can say that v prime squared is equal to c minus v squared. V prime is equal to the square root of c prime minus v prime. And that's just this. On the leg out, so if we're going from here to here, therefore that would just be a divided by the square root of c squared minus v squared. And on the way back, it's the same thing, it's just a little bit different direction. And that would be the same, that would be a divided by square root of c squared minus v squared. So now we know how long it takes to go from A to B and how long it takes to go from A to C. Recall that TAB is this plus this, and we're claiming that it equals that. Well, let's see if that's really true. Let's take the two terms separately, and so we would have A over C minus V. And we're going to multiply that by C plus V divided by C plus V, which is just 1, so we can do that. And that's going to give us, on the top, it's going to give us AC plus AV. And that's going to be divided by, well, C times C is C squared. V times minus V times C is minus C times this is plus CV. And then minus V times V is minus V squared. Well, this cancels, and so we would have AC plus AV divided by C squared minus v squared, that's 0. That's for the first one. So let's look at the second term. We would have a divided by c plus v. And this time we're going to multiply by c minus v over c minus v. Well, we should do it like that. That's going to be equal to ac minus av divided by, well, this is just the same as this. So it's going to come out to be that, c squared minus v squared. We have to add these two things together, and if we do that, we notice that we get 2ac here, but this cancels with that, that's 0. What we're just left with is 2ac over c squared minus v squared. So how do we get to here? Well, we can just multiply this by 1 over c squared divided by 1 over c squared, which is 1. This multiplication just gives us that. And this multiplication, that would be 1. That's v squared over c squared. That just gives us that. So yeah, TAB equals that. We've proven that. Now what about this? Well, this is over a common denominator, so you just add a to a, get 2a over that, and then we claim that it's equal to that. Is that true? Well, if we multiply this by 1 over c and this by 1 over c, so it's that multiplication gives us that. And this multiplication, we have to take the c into under the radical sign, so we have to square it, and c squared into c squared is 1, and v squared over c squared. And so, yep, we can say that TAC is equal to this. We need to understand under what conditions TAB is equal to TAC. If we take the ratio of them, this is the ratio, this is TAB and this is TAC. And if you remember your algebra, you take the extremes here and multiply them and put them on the top, and then you take the means here and you multiply them and put them on the bottom. This is just 2a times that, which is that, and this is just 2a times that, which is that. And we claim that it's equal to that. Let's see if that's true. Suppose that we multiply both top and bottom here by square root of c squared over v squared divided by the square root of c squared minus v squared. This times this is just c squared minus v squared. And we will notice something here, this cancels with that. Ultimately, we are left with 2ac over 2a multiplied on the bottom by the square root of, put this over here, of c squared minus v squared. And then we claim it's equal to that. Well, let's see, these two a's cancel, and we just have c over the square root of c squared minus v squared. If we multiply both top and bottom by 1 over c, then this cancels, and we get 1 on top, and we bring this under the radical sign, c squared and square it, c squared, that's 1, and that would be v squared over c squared. And that's that. So yeah, that's true. The ratio here is in fact equal to that. And then we can just multiply through by TAC and get this. And what that tells us is that TAB is equal to TAC if V is equal to 0. So there can't be any stream flow or ether flow. If it's 0, if there's no ether flow or the ether does not exist, then the times will be equal. But if V does not equal 0, then these two times are different. And that was the logic that Michelson and Morley used to build their device to test to see whether the ether existed or not. Here's a schematic of the device that the scientists used to test to see if the ether existed. How this works is that they send a source of light through here, and then they split it into two beams. One goes parallel to the ether flow, the other goes perpendicular to the ether flow, combined at a detector here. And what they were looking for is if they rotated the device 90 degrees, then the light that was going parallel to the ether flow would then go perpendicular to it, and the one that perpendicular to the ether flow would then be parallel to it. And that should change the times that the light took to take these trips to the detector. Well, why was that important? If you put a little prism here, for example, right before it hits the detector, you might see something like this. So if you just leave the machine stationary and don't rotate it, you'd see something like this. You'd see these light and dark bands here, these different color bands. But if you were to rotate the machine like this and the ether existed, then these bands here would be shifted over, called a fringe shift. So you can see here that the red band would move over here, the yellow band over here, the blue band over here. So there would be a shifting of these little colors or bands. And why is that? Well, if you have two waves, and remember they split the light wave into two waves, and another one here. Well, if these crests and troughs line up and they come to the detector at the same time after a rotation, you would just see the same thing before the rotation as afterward. So there would be no fringe shift, and so it would look the same in either case. But if the ether existed, if there was a flow, then one of the waves would speed up and the other one would slow down. And that would cause the crests and troughs to move past each other, and that would cause the shifting in the fringes. And that's what they were looking for. If the ether actually existed, they'd see this shift in the fringes, and if it didn't exist, they wouldn't see anything. The next question was, how much of a fringe shift would we likely see? How do you calculate that? Well, let's see. We know our TAB and our TAC time is this, and we need to find out the difference in the arrival times. We would have to take this and subtract this from it. This calculation is pretty ugly because of this square root here. We would like to find a way to make the calculation easier. And the way we're going to do that is we'll use a mathematical trick. This is the binomial expansion. That's what it's called. It's not important that you know anything about that, but it just tells us that we can write an expression like this in terms of the sum. We're going to let x, in this case, equal v over c. Squared is about 10 to the minus 8. That's a pretty small number. That works in our favor because when we look at these higher terms here, like x squared would be equal to 10 to the minus 8 times 10 to the minus 8. You add the exponents and that would be 10 to the minus 16. 10 to the minus 16th is a really, really small number. It's so small we can just ignore it. It doesn't add to the sum significantly, so we can get rid of that term. And that's true of every higher term. It doesn't add much to the sum, so we get rid of it. So we're just going to use the first two terms there to calculate our series. And this makes the algebra a lot easier. Remember, TAB was equal to 2LC multiplied by 1 over 1 minus v squared over c squared. This is the same as this. We can write that in this form. They're equal. So this expansion here just applies to what's in the curly bracket. I'm going to substitute v over c for x, which we did here. We're using a minus sign because there's a minus sign here. And n in this case is equal to -1. We do the same thing for TAC. Except n in this case is equal to -1/2. So we have our formula here, and we remember that TAB is that, and so we have 2 all over C. In the curly brackets, we have 1 minus n, but we know that n is equal to -1, so we put a -1 in there, and then for x, we substitute v squared over c squared, and that comes out to be this, because minus times a minus is a plus. We can say that TAB is equal to this as an estimate. And we can do the same thing for TAC. N is equal to -1/2, and so we can say that TAC is equal to this. The difference between TAB and TAC is that minus this. Well, we can factor out 2L over C, and we would get 2L C, and then we would multiply by 1 v squared over c squared, minus 1 minus 1/2 of v squared over c squared. But look, we can that goes to 0, so we're just left with these two terms, and that's what we have here. We can do the same thing, and this, say that that's equal to 2L over C would be 1 minus 1/2 v squared over c squared, and because we've just factored out the v squared over c squared, and we know what that is, that's 1/2. And the 2's cancel, and we're just left with this. The difference in the arrival times is equal to L over C multiplied by v squared over c squared. The distance between the arrival times of the two waves is proportional to delta t, and what do we mean by that? Well, if we have a wave, and this is the detector, and so we have the second wave that arrives late, and this distance here is d. And so, and this is the distance where the fringes go across one another, because this wave gets to the detector before this one. We can also say that the number of fringes in this distance here is proportional to the wavelength of light that's used in the experiment, right there. Now, why is that? If you have a wave, this is lambda, that's the wavelength. Or you could say that this is lambda. It's just the distance between two crests or two troughs. So we remember that delta t is equal to that, and we can set these two things equal to one another. So we would set c delta t, and that would be equal to n times lambda. So that would say that n is equal to c delta t divided by lambda. We know what delta t is, so we can substitute that in. That would be c times L over c times v squared over c squared, and then we'd have to bring this in. Well, this c cancels with this c, so the number of fringes is just L v squared over lambda c squared, and that's just that. So there we go. We know how many fringes will be shifted in our experiment. So here's the calculation done with the actual numbers, and remember our n was equal to this. Length of the arms of the apparatus in the experiment was 10 meters. So we put that in there. That L goes to there. And then V was 3 times 10 to the 4th meters per second. That was the velocity of the Earth through space, and we had to square that. The wavelength of light used in the experiment was 5 times 10 to the minus 7th meters. This goes to that. And then C squared is this, the speed of light. That's a homework assignment. You can do that calculation, but it comes out to be about 0.2. And since there were two waves, we have to double the number of fringe shifts, so it came out to be about 0.4. So that would kind of look like, here's the fringe before the rotation, and we would expect to see something like this, the fringe after the rotation. And that's what they expected to find. What was the result of the Michelson-Morley experiment? There was no fringe shift. Well, why did that create a problem? So if we look at our diagram here, this would be Bob 2, this would be Bob 1. We send a light signal at a certain time. The light goes down this way, and at that very same time, Bob 2 starts moving with a velocity v. The light signal arrives at his location right there, and the light signal arrives at Bob 1's location here because he doesn't move. this distance here is equal to x minus this distance here. There's no motion in this direction, so we can ignore it. There's no motion in this direction, so we can ignore these two things. But what's interesting here is that the times are the same. So the light arrives at Bob 2's location at the same time as the light arrives at Bob 1's location. Well, why is that? If we look here, we can compute the velocities somewhat like this. This is not really the way you're supposed to do this, but it'll work for our purposes here. This is what we have down here. Now, well, dx prime over dt prime, that happens to be c prime, and that's what we have here. Dx dt happens to be c, and that's what we have here. And then dt over dt, that's 1. So we just have v. The mathematicians can ignore what I just did, but it doesn't matter for this exercise. So we have this formula here, and then we can ignore that and ignore that. This is important. The reason light signals arrive at the same time is because c prime is less than c. The results of the Michelson-Morley experiment said c prime had to be equal to c. Why was that a problem? If the ether existed, then Galilean relativity was violated. And if it didn't exist, then the lines between particle-like and wave-like were blurred. Waves then could move through empty space, which at the time the conventional wisdom said waves couldn't do. So neither of these scenarios pretended a happy outcome. If the ether existed, then Galilean relativity was violated. If it didn't exist, then the lines between particle-like and wave-like were blurred. And that's basically what happened. The ether theory was eventually abandoned and replaced by the theory that particle-like substances could have wave properties, and wave-like substances could have particle properties under certain conditions and certain environments. That came along with the invention of quantum mechanics. Now, during this period, many physicists, reluctant to concede that the principle of Galilean relativity was wrong, suspected that Michelson and Morley had overlooked something, that a light wave could travel through empty space without some mechanism of transportation, violating all previous experimental results involving wave phenomenon, seemed to any reasonable mind improbable. Moreover, Galilean relativity had withstood the scrutiny of virtually all experimental tests. Its violations seemed equally improbable. An advocate of this view was the physicist Heinrich Lorentz. He argued that the length of the arms of the apparatus used in the Michelson-Morley experiment, shortened by a factor of L times square root of 1 minus v squared over c squared, when the arm pointed in the direction of the ether flow. The molecules in the arm were shortened in that direction. The contraction was just enough to account for the absence of the fringe shift and explained why the two beams arrived at the detector simultaneously. The slower light beam didn't travel as far. Lorentz also showed that his ideas were consistent with Maxwell's theory. Why did he make this hypothesis? Well, his solution preserved both the ether theory and Galilean relativity, so the physicists could have their cake and eat it too. Physics would not have to be completely reformulated because Galilean relativity was at the basis of Newtonian mechanics, and it was just unthinkable that Newtonian mechanics was wrong. Lorentz could not explain how the contractions actually happen. What mechanism made the contraction happen in the direction of the ether flow? And his critics pounced upon this and claimed that assuming the ether existed was superfluous, that the contraction theory provided no basis for believing that contractions actually happen. So there must have been a better solution. And after a break, we're going to talk about what that solution is. Okay, we're back. So what is the twin paradox? Well, it arises from something called the principle of relativity. And the principle of relativity is what Einstein used as a basis for his theory of relativity. In particular, his theory of special relativity. What does the principle of relativity say? Well, it says that it's impossible to determine whether S, this would be Bob 1, is at rest, and S prime, this is Bob 2, is moving in the plus x direction, or S prime, which is Bob 2, is at rest, and S is moving, this is Bob 1, in the minus x direction. In other words, both twins can claim to be at rest while it's the other twin that's moving. So what we have here is, this would be Bob 2, Bob 1, and they would be moving at a velocity v relative to one another. In this case, Bob 2 could claim that he was at rest, and therefore Bob 1 would be moving in that direction. And if Bob 1 is at rest, then you would have Bob 2 moving in that direction. What was the consequence of the principle of relativity? Well, we could say that x prime is equal to c prime t prime, and we can say that x is equal to ct. So if you'll notice something, we can say that x is equal to x prime plus vt. This plus that. That's equal to that. But then we know that x prime is equal to ct prime. You can write that x is equal to ct prime, substituting ct prime in for x prime, c prime t prime, sorry. And then we add to that vt. But then x is equal to ct, so for x we can substitute in c times t, and then other side of the equation just stays the same. If we move this over to the other side of the equation, we get this, and that's equal to that. I should talk about this equation. If t is equal to t prime, then c prime has to be equal to c minus v, and that was consistent with Galilean relativity. The Michelson-Morley experiment said that c prime is equal to c, so we'd have to substitute this in, c for c prime. And what that does, the only way that this equation could be true is if t is not equal to t prime. The times could not be the same. In particular, t prime would have to be less than t. And this was the consequence of the principle of relativity. And ultimately, that's what Einstein concluded. Recall our formula. C minus v times t is equal to c prime times t prime. This was Bob 1 from his perspective, and this is Bob 2. Moving stationary. If it was true that c prime had to equal c, then one of the two twins was measuring time incorrectly. From Bob 2's, this is Bob 2, from Bob 2's perspective, x, this distance here, is equal to x prime plus vt prime, measured on Bob 2's clock. And from this perspective, or this would be Bob 1's perspective, then this distance here is equal to x minus vt, this minus this. And gamma here in this instance represents the error that Bob 2 thinks that Bob 1 is making in measuring the distance. And it's also the error that Bob 1 thinks that Bob 2 is making in measuring this distance. So let's see what the consequences of that is. We have to solve and find out what the value of gamma is. And how we do that is we just multiply them together. So we take x times x and we get this. Take that times that and get that. And then we multiply that times that, which is that times that. X prime times x, that's that. X prime times minus vt is that. X times vt prime is that. Vt prime times vt is just that. So we have to remember something, that t prime is equal to x prime over c. This would be, since that's equal to c times t prime, then t prime is equal to x prime over c. And the same thing you can say ct. And so we can conclude that t, is equal to x over c. We can take this formula and plug in x prime over c for t prime and x over c for t. We plug in x over c for t prime, and that's how we get that. And we plug in x prime over c prime in for t prime, and that's how we get that. And these two terms just stay the same. Carrying all this forward, we now have this, but we'll notice something, that this term and this term are equal except for sign. So they add up to 0. And that just leaves us with this term and that term. Bring that down. The next thing we can do is multiply through by x prime. We can divide this by x prime, and divide this by x prime x. I switched them, but that doesn't matter. All right, so what do we get here? Well, this divided into that is 1, and that's going to equal gamma squared. This is going to be 1, which is that, and these are going to cancel, which gives us that. So that says that gamma squared, I better make a gamma here, gamma squared is equal to 1 divided by 1 minus v squared over c squared. And if we take the square root of that, we just get this. Plus or minus, but we'll just take the plus. And so that's 1 over the square root of that. And that's the value of gamma. So if we remember our two equations here, if Bob 2 is at rest, then we use this formula because Bob 1 is now moving. And we know the value for gamma, so we just can substitute in this value for gamma. And that's what we get. And if Bob 1 is at rest, Bob 2 moving, then again we can just substitute the value in for gamma. So that gives us Bob 2's position relative to Bob 1 who's at rest. And we can also solve for the time. So here if we bring this equation down, that's that, we have to remember that E is equal to x over c. We can substitute x over c in for t, and we get that. And then if we just multiply both sides of the equation by 1 over c, we get 1 over c times x over c minus v over c squared times x. We know that x prime over c, that's equal to t prime. So we can get rid of that. That's equal to t. That implies that t prime is equal to gamma times t minus v over c squared times x, and we just plug the value in for gamma. This tells us the time on Bob 2's clock, who is moving in this case, in terms of the time on Bob 1's clock. We can do the same thing for Bob 2 is at rest and Bob 1 is moving. T prime is equal to x prime over c, so we just substitute that in. Multiplying through by c, we get this, remembering that x over c is t, and remember that t prime is equal to x prime over c. We can just substitute it into here, and this gives us the time on Bob 1's clock, and Bob 1 is the one that's moving, so we can set up a relationship between Bob 1's clock and Bob 2's clock. Those four equations that we just talked about are called the Lorentz transformations, and they're used to determine the time on a moving clock relative to a time on a stationary clock, which is not the same, by the way, according to the principle of relativity. Here are our twins again, Bob 1 and Bob 2, and they're going to explain the twin paradox. Here are our twins, Bob 1 and Bob 2, and we're going to put Bob 1 on Earth and Bob 2 in a spaceship. Bob 2 is going to fly around for a while and come back to Earth, and we'd like to ask the question, how old is Bob 2 relative to Bob 1 after the trip? We're going to use these simple equations. Where do they come from? Well, if we remember our Lorentz transformations, we would have t prime is equal to gamma times t minus v over c squared x. This would be Bob 2 moving. This side would be Bob 1 at rest, stationary. Now we can write another one for the opposite. Bob 2 can be considered at rest and Bob 1 at moving. And so what that equation looks like is just t is equal to gamma times t prime plus v over c squared x prime. This x here, we can always choose a coordinate system such that x, in this case, can be set equal to 0. Since Bob 1 is at rest, we can just pick the most convenient place for him to be, and since he's at rest, he doesn't move, he stays right there. For the whole thought experiment, he just stays at x equals 0. That's his position. And that makes it really convenient because this term vanishes. It goes out at 0. We can do the same thing down here. Remember, this is Bob 1 moving, and this is Bob 2 at rest. We can do the same thing down here and say that x prime is equal to 0. And that gets rid of that term. This term becomes 0. All we're left with is this part and this part. Well, that's the same thing as we have over here, except we've substituted, or we've renamed t prime to be the time on Bob 2's clock, and we've remember gamma is equal to 1 divided by the square root of 1 minus v squared over c squared. And here we've just replaced t in this case with the time on Bob 1's clocks. This equation marries up with that one, and then the opposite is true of this one. This equation marries up with that one. So let's see what happens. So we send Bob off on a trip, and he spends 1 year flying around space, basically in a straight line, although it looks like a circle here, at a velocity of 3/5 c. All right, so let's use this equation up here to determine how old Bob 2 is relative to Bob 1. So we do that. We have Bob 2 is equal to gamma times the time on Bob 1's clock. So now if Bob 1 travels for a year on his clock, he's stationary relative to his clock. If he spends a year, this becomes 1. We can say that 1 is equal to gamma. Well, we can write gamma as 1 over square root of 1 minus v squared over c squared times t1. So we can say that t1 is equal to the square root of 1 minus v squared over c squared. Well, we could just ask Siri or Alexis to figure this calculation out for us, but that's what the millennials would do. But for us technically challenged baby boomers, we'll do the calculation out. But we know what v is. V is 3/5 c from up here. And so let's plug that in, and so we get the square root of 1 minus 3/5 c over c squared. Well, that says that t1 is equal to the square root of 1 minus 3/5 squared, but 3/5 squared is 9 over 25. 1 minus that is the square root of 16 over 25, but that is equal to 4/5. And the reason that is because the square root of 16 is 4 and the square root of 25 is 5. The time on Bob 1's clock is 4/5 of the time on Bob 2's clock. So Bob 1, which is 1 year. So Bob 1 thinks that Bob 2 is younger, and that's a result of the principle of relativity. But remember what the principle of relativity says. It says that Bob 2 can consider himself at rest, and Bob 1 is the one that's moving. And if that's the case, we have to use this formula. And if we did that, we'd go through this whole rigmarole again. The time on Bob 2's clock would be 4/5 of a year, 4/5 year, and the time on Bob 1's clock would be 1 year. Now Bob 2 thinks Bob 1 is younger. And how can that be? How can it be that both twins think that the other one is younger? So we have our formulas here. We have T2 is equal to gamma T1. That's Bob 2's clock moving, or Bob 2 moving and Bob 1 at rest. And we have the other formula, T1 is equal to gamma times T2. By the principle of relativity, we can consider Bob 1 to be at rest and Bob 2 moving. These two formulas are equal. We have two equations and two unknowns we can solve and see what we get. We would have T2 is equal to gamma T1, but we know what T1 is. That would be equal to gamma times gamma T2. This becomes gamma squared T2. Well, we can cancel on both sides of the equation here, and we would get 1 is equal to gamma squared. Oh, what's gamma squared? That implies that 1 is equal to 1 over the square root of 1 minus v squared over c squared, which we can write as 1 minus v squared over c squared square root is equal to 1. And we want to ask the question, well, how do we make this equation true? It's pretty clear that in order for this equation to be true, v would have to be equal to 0. If v is equal to 0, then you get square root of 1 equals 1, which is true. What happens, though, when v does not equal 0? Well, let's see. Say that v equals 3/5 c. What happened? That would be 1 minus 9/25 equals 1. Well, that would imply that square root of 16 over 25 would be equal to 1. Well, that would imply 4/5 is equal to 1, or that 4 is equal to 5. Now I'm going to bet that at least 10% of the physicists at the Institute for Advanced Study would reject this. Well, physicists make statements like 4 is equal to 5 all the time, but what they really mean is that 4 is a good approximation for 5. They don't mean that 4 equals 5, and probably no mathematicians would go for this. So there's clearly something wrong here, and we have to determine why this paradox occurs. This is actually the twin paradox illustrated in mathematics. 4 can't equal 5, so we have to try to figure out what's going on. Now, if you've seen twin paradox videos before, you've probably noticed that some of them use a third observer, and then they work out a bunch of complicated mathematics. It's pretty hard to follow. I'm not going to use complicated mathematics. I'm just going to use simple formulas that we've used before, and we can remember this is the moving twin, the arrest twin over here. The same way. It's the same thing here, moving rest. But I am going to introduce a third observer, and I'm going to call her Alice. There she is. And she's going to be our official timekeeper. And so we're going to use Alice to see if we can resolve this contradiction, this paradox that arises because of the principle of relativity. Let's say we do a thought experiment. Alice, Bob 1 and Bob 2 are all 10 years old at the beginning of this thought experiment. And so Alice has to choose which one, Bob 1 or Bob 2, that she wants to ride with. She could either ride with Bob 1 or she could ride with Bob 2, and she has to pick. She flips a coin, it comes up heads. She decides to pick Bob 1 to ride with. The thought experiment goes like this. One of the twins is going to go out on a journey at 3/5 the speed of light and then instantaneously turn around and come back. Now, we can't have any acceleration in the special theory of relativity, so we have to cheat a little bit here and assume that the twin can instantaneously turn around. Alice, since she's riding with Bob 1, she can't really tell whether she's the one that's taking the trip. But what she can tell is that her clock is moving at the same rate as Bob 1's clock because they're at rest relative to one another. She can consider Bob 2 in this first leg of the trip as the one who's moving. Bob 2 starts out and he goes out after 5 years on Alice's and Bob's clock. Bob 2 he turns around and he comes back, and this is 10 years past measured on Alice's and Bob 1's clock. But because Bob 2 was the one that was considered moving relative to Alice's and Bob 1's clock, he is only aged by 8 years since he's traveling at 3/5 the speed of light. After 10 years, we have to add 10 years to Alice's age, so she's 20. We have to add 10 years to Bob 1's age, and he becomes 20. But we only add 8 years to Bob 2's age. He's only 18 years old after this. Alice can trade places. She can now decide that she's going to ride with Bob 2 and do the same thought experiment, except this time she's riding with Bob 2 and it's Bob 1 who takes the trip. This is 5 years. This is another 10 years. Bob 1 now goes out on this trip, instantaneously turns around and comes back, and on Bob 2 and Alice's clock, 10 years have passed. But on Bob 1's clock, only 8 years, because that's 4 and that's 4. He goes out and comes back. It only takes him 8. So we have to add 10 years to Bob 2's age, and he becomes 28 years old. We have to add 8 years to Bob 1's age. He becomes 28 years old. But we have to add 10 years to Alice's age. She's 2 years older. She's 30. And so the twins are twins again. However, Alice is 2 years older. The twin paradox arises because we think that Alice can ride with both Bob 1 and Bob 2 at the same time, which she can't. But if Alice could ride with Bob 1 and Bob 2 at the same time, his x prime would be equal to x and t prime would be equal to t, because her clock would be at rest with both Bob 1's clock and Bob 2's clock at the same time. This is Bob 1 moving and this Bob 2. And in this case, this is Bob 2 moving. And here, this is Bob 1 at rest. So if that's the case, we'd use this formula. Alice gets to ride with them both at the same time. We can substitute x in for this, and we can substitute t in for that, because they're equal. She's riding with both Bob 1 and Bob 2 at the same time. We can then say that x plus Vt divided by this is equal to this. I'm just going to divide this thing up into common denominators, so that would be x over the square root of 1 minus v squared over c squared, and then we would add to that v over t divided by the square root of 1 minus v squared over c squared. And that would be equal to this side of x divided by 1 minus v squared over c squared, square root, and then we would add to that this part, that would be a minus, and that would be v over t divided by square root of 1 minus v squared over c squared. Okay, so you notice something here. This cancels with that, and so what are we left with? Well, we're left with v over t over the square root of 1 minus v squared over c squared, and that's going to be equal to minus vt, this part, divided by 1 minus v squared over c squared square root. Well, you'll notice something here, that these two amounts are the same, they just have a different sign, so we would cancel, and this is what we would get. I'm going to double down and say that the physicists at the Institute of Advanced Study, at least 20% of them wouldn't go for this. No mathematician would go for this. Now, the only people who really like this result are the politicians, because they may have a deficit of $1 trillion in their bank account, but that's the same thing as saying that you have $1 trillion to spend. So politicians are big believers in the twin paradox when it comes to budget resolutions. This is what happens when we think that Alice can ride with both Bob 1 and Bob 2 at the same time. And if we reject that premise, which we should, we wouldn't get this. 2 was claiming to be at rest, and we would have to use this formula if Bob 1 was claiming to be at rest. But we couldn't use them at the same time. That's my solution to the twin paradox. So we're back. Evidently, the world can be divided up into people who are believers in the twin paradox and those who are non-believers. Those people who want the government to run things as though 4 does not equal 5 are usually called liberals. They want to control everything. And they can usually give a pretty good logical reason why 4 doesn't equal 5. They're very scientific in their thinking. The facts are that 4 does not equal 5, and so you shouldn't run the world like this. It's got to be run like that. Unfortunately for them, the government is run by politicians who are perfectly willing to say that 4 does not equal 5 or 4 equals 5, depending on how much money you want to contribute to their re-election campaign or vote for them or something like that. Usually the politicians just try to locate somewhere where there are more liberals than conservatives or vice versa, and then just tell the people what they want to hear. But then you are never really sure if the politician is sincere or not. Politicians tend to frustrate the liberals. That brings us to the religious or conservatives, and what they're after is certainty. The Jehovah's Witnesses, for example, are absolutely sure that whatever their literature says, however contradictory, is true. Religious conservatives have, for the most part, accepted God as their personal savior, and in return, they believe that he's promised them everlasting life. This is a certainty. So what does God do? He comes down and says, the world is either this way or that way, you pick. He forces our conservatives to have a free will. And they don't want a free will. They want certainty. So God kind of treats these people badly there, giving them a free will when they don't want one. And then that brings us to semi-religious or maybe non-religious conservatives. And they really endorse this idea of a free will. Newt Gingrich is one of these. He's got a grandmother. She must be 150 years old by now. And she's not happy unless she's making choices. She seems to choose mostly health insurance policies, but I'm sure she makes lots of other choices too. Rand Paul is another one of these types of people, but usually there's a catch. Us conservatives want the government to pass laws that ensure that people make the right choices. So if you want an abortion, that's a choice, but that's the wrong choice, so you can't do that. And if you want to marry someone of the same sex or gender, that's a choice too, but you can't do that one either. Us conservatives are often viewed by liberals as being hypocritical. So I bet you didn't think that the twin paradox had so much to say about life. Well, it really doesn't. This is just my shameful attempt to get people to watch my video by insulting as many groups of people as possible, because my president says that if nobody watches my videos, then I'm a loser, and I don't want to be a loser. So there you have it, the twin paradox. So now that you're feeling really good about yourselves, be sure to check out my website at www.roadtoatoe.net. There you'll find something called 4 Reflections. It refers to 4 books that you can download for free. The books discuss attempts to unify general relativity with quantum mechanics. It's usually called the unification of physics. So if you're interested in that subject, there it is. So until next time, you conservatives and liberals out there, have a nice day.